Welcome to Chem Help ASAP. Let's focus on the factors that cause proton coupling as observed in proton NMR spectra. So what are the factors that affect the resolution, peak position, and multiplicity of signals in an NMR spectrum? We'll discuss three factors. First, the sample sits in a magnetic field. This is an image of an NMR tube. The lines at the bottom represent the coil of the electromagnet. The symbol for magnetic field is often a letter B with a bar over it. The field of the magnet is often called the applied field. A higher field gives a higher resolution. That means better separation of the peaks in the spectrum. The second effect is the localized electronic environment around each hydrogen nucleus. Electrons are moving charges and create variations in the overall magnetic field. I'll call this effect BENV for environment. Differences in the environment around hydrogens give rise to differences in the chemical shift of hydrogens. Lastly, proton nuclei have a spin up or spin down, and generate their own magnetic field. A proton nucleus can influence the magnetic field of a neighboring nucleus. I'll call this B neighbor. This is the effect that gives rise to coupling. Let's see how all these factors work together. Here is a molecule with just two hydrogens, and they are vicinal neighbors. We're going to see some coupling. Let's assume we are observing the right hydrogen. So the left hydrogen is the neighbor. This hydrogen, the right hydrogen, will feel the applied field. It will feel some local electronic effects. It will also feel an effect from the neighboring hydrogen. The observed magnetic field, OBS, will be the sum of these contributions. Here comes the coupling effect. Remember that the neighboring hydrogen has two possible states. It can either be spin up, and that's plus B neighbor. It can also be spin down. That's minus B neighbor. So our hydrogen, the right hydrogen, has another possible B observed value from the same equation with a minus B neighbor. Keep in mind that within a sample are likely billions of molecules, each with one of our hydrogens. About half those hydrogens will have a spin up neighbor, and about half of those hydrogens will have a spin down neighbor. These two B observed values will be about equivalent in population. What does this mean? Our hydrogen is in the applied field, and the chemical shift is determined by BENV. At the chemical shift, the signal will appear as a split peak, two separate peaks based on the influence of the neighboring hydrogen. Let's see the spectrum. Here is the spectrum. The signal for the proton next to the bromines is upfield at about 5.2 ppm. Note that the signal appears as two peaks in about a 1-to-1 ratio. The chemical shift is at the midpoint of this doublet. The other hydrogen, the proton next to the chlorines, is downfield at close to 5.8 ppm. It is also a doublet with about a 1-to-1 ratio because this hydrogen also has a single neighbor. That was an introduction to the origin of coupling in proton NMR. If you enjoyed this video, please leave a like and consider subscribing. Questions, comments, feedback, please use the comment section. Take care.